Friends, we are back with fluorescence spectroscopy again. So, in our last lecture, we have started discussing this electron transfer. So, we'll and we also talked about the importance of this process, this electron transfer process. Now, here we will just deal with simple models, by which we will try to understand what is it happening. What is this electron transfer? What is meant by electron transfer? Then the famous Marcus theory of electron transfer. The associated terms are like reorganization energy and adiabatic, non-adiabatic factors. Okay, these are the things that we will take up. Now electron transfer, this this electron is transferred from donor to acceptor, this electron. So, giving rise to this charge transfer state. It is a di-radical, a radical ion. This is one radical ion, this is another radical ion. Okay. So, this is D, this is A. So, and the electron is transferred from here to here, so that you have D plus dot and A minus dot. So, this is your charge transfer state, normal charge transfer state, and this is your ground state. So, till now we have not utilized anything, like anything like photon. So, suppose if the situation is such that this your acceptor is state is not here, but it is somewhat up over here, then this direct transfer of electron from here to here may not take place because of this energy considerations. Okay. So then what you can think of, in this case, if it is over here, then it is your highest occupied molecular orbital. It was initially highest occupied molecular orbital. Then when you shine with radiation, then photo-induced electron, this excitation of this electron from here to the LUMO, and then from LUMO to this to here. So, this is your locally excited state. Originally, in previous diagram, it was over here, but when it is shifted over here, then this prescription will not work. Okay. So, so you get your LUMO, then LUMO to this home, LUMO of this acceptor. So, it is your locally excited, then it gets to here. So, giving rise to D plus dot and A minus dot. So, this is also a charge transfer, but the point is this is the earlier one was normal, ground state electron transfer, like what you do in chemical laboratory without light, that some oxidant, some reductant, if you mix together, then you will have chemical reaction. Okay, but here, in those cases electron transfer takes place in the ground state, but here the electron transfer takes place in the due to photo-induced, it is basically a photo-induced electron transfer. The electron is initially promoted to higher level of the donor, and then it is transferred. Okay. So, again, charge transfer, electron transfer, hole transfer, these are the three things that generally happen. So, electron transfer. Okay. So, this is your initial state, and this is your final energy diagram. Okay. So, you see, and this is your intersection, that is your transition point. In some cases your crossing is avoided, that is here they are not crossing. In some cases, you will be finding that the crossing crossing is there. Okay. So, So, it is the electronic coupling, HIF is the electronic coupling between these two, initial state and the final state. This is dA state and this is d plus dot A minus dot. Okay. And this is your what? This is your normal, I mean activation free energy. Okay. So, so how to calculate delta G double dagger is delta, I mean G double dagger minus G0 I. So, this one, that is why this gap, and here it is delta G 0 equal to G 0 final minus G 0 initial. Okay. And this is your energy and this is your the reaction coordinate. So, the rate of electron transfer is is having this expression where your delta G0 is this, okay. Lambda is a term what is called your this reorganization term, okay, and beta is the attenuation factor, it is the Boltzmann constant, okay. So, HIF is the electronic coupling, that is the overlap, electronic overlap, and when it is under adiabatic limit there is a large probability of crossing to the other surface. So, from one surface to other there is large probability, non-adiabatic there is a small probability of crossing. So, if you want to learn more, then you can consider this, I mean you can go through this article. Okay. So, starting point, then it crosses, I mean it gets transferred from initial to the final surface. Okay. Now, this HIF is this one, I mean it is in the expanded form, okay, and here where you see that crossing is avoided. Okay. So, this is your classical activation free energy and this is your delta G 0 of the reaction. So, this is your initial surface, this is your final surface. Okay. Now, so this is your in normal case you see that previously in the previous diagram you see that dA is upper and d plus dot A minus dot is in lower, but here in case of photo induced electron transfer what you see that this diagram is changed. Okay. So, what has happened is that now you have photo excitation, okay, photo excitation, and this is D, this is A in the ground state and D star A, it is in the excited state of D and A. Okay. Now, you have this is your initial state and this is your final state. Okay. So, you see that delta G double dagger which was originally, I mean it was over here, I mean this one is now modified to this value, and now the crossing is over here, and your corresponding delta G 0 for the process where one is D star, another is A is this, okay, and delta G 0 is equal to F into this one, this is your D plus D, that is your oxidation potential, and this is your reduction potential of A, and this is your delta W, and this is your 0 energy, and delta W has got this expression ZA ZD minus E into E square. Okay, they are corresponding charge. So, this is like E square by R, like Coulomb kind of expression. Okay, that is Coulomb expression. Okay, so it is one is reduction potential and the other one is also, I mean this is both are the half cell reduction potential. Okay. Now, now Marcus theory, it has got events like electron transfer, then molecular reorientation, then solvent reorientation. These are the factors that always come. So, D plus plus A giving rise to D plus plus A minus with rate constant KEL, I mean electron transfer rate constant. So, KEL has got, I mean, 3 terms. One is this related to the nuclear vibration frequency, where VNR is the nuclear vibration frequency, KELR is the electronic transmission factor, that is electronic coupling, which contains in particular the distance between D and A and the nature of chemical functions located in between D and A, that means the spacure between D and A. So, that is your electronic transmission factor. Okay. So, this is the second term, and the third term is the nuclear factor. Okay. So, thermodynamics of process and reorganization parameters. So, these are the you know, ingredients of this electron transfer rate. Okay, these are the ingredients of electron transfer rate. Okay, so we have started with Marcus theory. So now next comes is your electronic factor. So I mean KEL is basically, I mean, this electronic factor, this electronic transmission factor. So that is proportional to HAB square, that is mod square of HAB, and HAB being the coupling matrix element or the coupling Hamiltonian. So and where HAB is H0 into exponential to the power minus beta. So HAB basically reduces exponentially. Okay. So that means with distance it will fall rapidly. Okay. And here I mean, if we plot this one HAB as a function of R, then it will be exponentially decaying. Okay. What are the other terms that is there in HAB? So, HAB is equal to H naught, some you know H naught is basically when R is I mean, it is this it is a steady value that will be achieved, that is your exponential to the power minus beta R. Okay. So, maybe at 0 value of R. Okay. 0 value of R, whatever number you will be getting, that is your H0. Okay. So, it falls up rapidly. This is your attenuation factor, this beta is called your attenuation factor in angstrom inverse if R is expressed in angstrom. The nature of the bridge or the spacer, so it is your donor and say you have got the acceptor. So, this is your bridge, or it is called the spacer between D and A, will determine the coupling and it is quantified by beta. Okay. So, that is called your attenuation factor. If beta is 0.1 or 0.2 angstrom inverse, the electronic coupling is very strong and the electron can travel over very large distance, like aromatic or conjugated bridges between D and A. Okay. So, when coupling is very strong, when coupling is strong, then like in case of aromatic or conjugated bridges between D and A, so electron can travel a large distances. If beta is like 0.8 to 1 angstrom inverse, then D and A are only slightly coupled and the electron transfer rate will fall off very rapidly. In a few angstrom, electron transfer rate will almost go to 0. So, when beta is 0.8 to 1. So, in the higher range of beta, if it is close to 1, then it will fall off rapidly, but if it is less, then this attenuation factor, I mean, if it is less like 0.1 and 0.2, then it will be, you know, it will be coupling will be very strong. Okay. The nuclear factor. So, Kn is the nuclear factor, Kn is equal to exponential to the power minus delta G double dagger by RT. So, where delta G is your classical activation barrier. This is your classical activation barrier, and think of this that this is your reactant surface and this is your product potential energy. So, this is D plus A combination, so for your reactant and this is for your product, and this is your delta G double dagger. Okay. So, this is your this nuclear factor, this Kn is related to e to the power minus delta G double dagger by RT. So, this delta G is the classical activation barrier, that is your transition state, and this is your the lowest point, excluding, this is the starting point, energy point for your reactant. So, exactly it is not over here, because you should have considered this 0 point energy. So, it may be a little above this 0 line. So, this to that gap is your classical activation barrier, that is what you can understand classically. Okay. Now, Marcus quadratic equation is delta G double dagger. Delta G double dagger is basically lambda by 4 into 1 plus G 0 by lambda whole square. This is your quadratic equation. Delta G 0 is the free energy difference between the reagents and the product. Delta G is negative for any and delta G is negative for any spontaneous reaction. So, this is the free energy difference between reagent and the product, and delta G is negative for any spontaneous reaction. What is lambda? Lambda is called the reorganization parameter. Now, what is this reorganization parameter? Now, this reorganization parameter is basically it is a measure of the energy cost that the system would have to pay to undergo the distortion or reorientation leading to the product from the reactant, okay, when there is no electron transfer. Okay. So, and basically what is reorganization means, suppose you have got say you have a transient dipole which is created in some solvent, okay, maybe in water, in a polar solvent. Okay. Initially there was no dipole, okay, but immediately after the creation of the dipole, what will happen, that the water molecules will feel or will face some electric field, and as a result of that, this water dipoles will tend to reorient themselves so that the energy gets minimized. So, that means solvent molecules are reoriented as a result of this creation of this transient dipole. So, this reorganization is related to this term. So this that's why it is a measure of the energy cost. In order to reorient this water dipoles, some energy is required, and that energy is arising out of this reorganization or reorientation of solvent molecule, and it is termed as reorganization. So, it is a measure of the energy cost that the system would have to pay to undergo distortion or reorientation leading to product from the reactant. So suppose if this is a product, if this is your product, that is initially there was no dipole, but suddenly the dipole is created, then this is your product. So, in order to stabilize this dipole, these water molecules should reorient, and some energy term is involved, and of course, this lambda, this reorganization parameter corresponds to the case when there is no electron transfer. Okay, when delta G 0 equal to 0, that means practically there is no difference, there is no difference in energy curves for the reactant and product. So, delta G equal to 0, and this lambda is this, basically this is your reactant side and this is your product side. So, in order to reach this this product surface some distortion or reorientation is necessary. So, that is denoted by this vertical line. So, this is your reorganization energy, or this is called your reorganization parameter. Okay. So, now in general delta G 0 is not 0 in general, but if delta G equal to 0 means basically reactant and product surface are at the same level. Okay. So, if you consider this diagram, that this is your reactant surface, okay, and say this is your product surface. Okay. So, you see here this is your transition point, okay, I mean transition state. This is your minima for the reactant surface, and this is the minima corresponding to the product surface. So, this is your delta G 0 and this is your lambda, and you see that the product surface is shifted in the right hand direction with respect to the reactant surface. So, now this lambda, what is this lambda? This lambda contains two distinct terms. One is internal reorganization parameter, that is maybe internal coordination sphere related to internal coordination sphere, or maybe internal readjustment of the molecule, and out is basically related to the solvent or the environment. So, that is to account for the solvent molecule, the counter ions, etc., etc. So, lambda is reorganization energy, okay, reorganization parameter that has two terms, one is lambda in plus lambda out. Okay. So, lambda in means internal reorganization parameter. So, it is internal, and these are outside or external, especially to this maybe solvent molecule or maybe something else, I mean maybe counter ions. Okay. So, this is one type, I mean situation when R and P they are disposed in this fashion. So, this diagram says about I mean explains which term is called delta G double dagger, which term is delta G 0 and which one is lambda. So, delta G double dagger is the activation free energy. Okay. Okay. So, increasing the driving force, what is going to happen? If we increase the driving force, that means more negative delta G. Okay. More negative delta G means here your delta G 0. So, it was like this much, it was like this much. Okay. Now, what you do, you drive this to, I mean if you take it to some lower situation, this is your reactant surface, this is your product surface. Okay. If you drag to the lower side, so that this difference is more, initially it was less. So, basically delta G 0 thermodynamically, I mean delta G 0 is a measure of it is ultimately related to your equilibrium constant. So, that means driving force, that is if delta G is more means more negative means driving force is more. So, in that case if driving force is more, then you see that your initial activation barrier was like this. Now, this activation barrier has reduced. Okay. So, increasing driving force of a reaction, then reaction becomes faster. So, in that case if the activation barrier decreases then reaction becomes faster. Okay. So, so this is important, I mean this driving force is very important for the reaction, and if increase of driving force is related to the decrease of the barrier height, barrier means this barrier height, then reaction becomes faster. Okay. So, if you continue to increase the driving force, that is minus delta G is 0. Okay, that is delta G is 0, I mean in terms of minus value. So as to, I mean, if you reach a situation that you see, if you think of I mean here, like you have got one potential energy surface, like, and of course in that case you approximate this potential energy to harmonic oscillator potential energy, so that your description will be, I mean model will be easier to describe. So that is why we always take this reactant potential energy or the product potential energy as to, I mean equivalent to the harmonic oscillator approximation. Okay. So, you know what you do, so this is the product surface. So, this activation energy is delta G, this one, but if it is over here, suppose then your activation energy will be over here. So, that means your activation energy is more. Okay. So, this way if you keep on, you know, dragging it downward, I mean it is not that you by your choice you are dragging, the situation is such that, or maybe you are choosing, you know, such a donor acceptor pair, or you are varying some of the parameters in the donor acceptor pair, that it is dragged progressively downwards. Okay. So, a situation will be reached eventually that, you know, you will be getting this situation. You will be getting this situation, that you see that it is you know activation less it is. So, your basically so in that case you have lambda is equal to minus delta G 0. Okay, it is an activation less, activation free situation. Okay, so that your delta G double dagger is equal to 0 and lambda equal to minus delta G. That means your reorganization is exactly equal to minus delta G 0. Okay. So, in this way, means if you keep on, I mean changing this, I mean you play with parameters of this I mean donor and acceptor pair, so that this second potential energy surface or the relative position of the potential energy surface is changing. Okay. So that, you know, you can have different situations. Okay. So, we have got an activation free situation or activation less situation, that is your delta G double dagger is equal to 0. So, under this condition. Okay. Now, what is then Marcus inverted region? What is then Marcus inverted region? So, that we should you know try to understand. Now, if we keep on doing this, so that it is progressively shifted this direction, then another situation will come that, I mean that you have your second surface like somewhere over here maybe, so that now it is no longer okay, this delta G double dagger is not equal to 0, but it is very thin, very small, but still it is there. I mean some delta G double dagger is there, I mean it is not exactly equal to 0. So, when reaction is more and more favorable thermodynamically. So, when you drag this way I mean from here to here, okay. So, that thermodynamically more and more favorable, the rate of electron transfer, you know, you will be finding that here, although it is thermodynamically favorable more, but the rate of electron transfer has been found to decrease. Okay. So, classically, you know, this is it is not possible to understand classically that why, you know, electron transfer rate should decrease after a certain point, even if the reaction is thermodynamically, I mean electron transfer is thermodynamically, I mean classically more favorable. Think of classical thermodynamics, then it says that it is more favorable because it is only on the basis of delta G 0, that the more the negative value, the more favorable the process is. So, that is not easily understandable why this is happening. So, basically, you know, if you plot electron transfer rate as a function of, you know, lambda, or as a function, I mean what is happening, that this is k E t, and then you will be finding, I mean if you plot with respect to this delta G 0, then you will be finding that initially electron transfer rate increases, then maximizes, then it starts to decrease. So, this is your normal region, and this is inverted region, which you cannot, you know, simply understand why this should be there. Okay. So, classically the rate of any reaction is expected to increase with the driving force. So, there is something that we cannot simply explain from the basis of this classical thermodynamics. Okay. That is, the rate of electron transfer decreases even we increase the delta G 0 value. Okay. Okay. So, you see that here again, let us look into this figure, that this is your delta G 0 is not 0, I mean exactly not 0, I mean this is, although it may look like means it may appear to you that maybe it is still at the lowest point, but maybe if we you know microscopically observe it, that maybe this value is not exactly 0, it is nearby 0, but not exactly equal to 0. But if we keep on shifting this r, maybe this direction or maybe this one in this direction, then again you see that delta G double dagger increases. So, diagrammatically it is very clear that again in this side we were increasing, that means your delta G 0 was reducing, but here when we are shifting this way, although we are increasing delta G 0, but delta G double dagger is not, you know, is not 0, but it has got some, you know, some barrier height. Delta G double dagger relates to the barrier height. Okay. So, this region corresponds to, in this region where you have again your delta G double dagger to be not equal to 0, but electron transfer rate is reduced. So, this region is called, I mean your Marcus inverted region. So, normal versus inverted. So, it is your KET, this is your inverted region, and this is your a normal region. So, where electron transfer rate is increasing and then electron transfer rate is decreasing. Okay. So, plotting in terms of you know this way. So, you see that when this is equal to 0, okay, this is equal to 0, delta G, I mean at the inversion point, delta G double dagger equal to 0 means delta G 0 equal to minus lambda, okay, delta G 0 equal to minus lambda. So, one side is inverted, another side is the normal region, okay. So, this is your normal versus inverted region. So, so experimental confirmation, I mean if we plot, then you see that electron transfer rate, you see if we plot, I mean with your naphthalene, okay, then this molecule, I mean you are increasing this spacer, I mean this, as I told you that it is polyaromatic. There are two in this case 2 benzene ring, 3 benzene rings, 4 benzene rings. This way you keep on increasing, you see that electron transfer rate is more and more, okay. So, go back to the earlier slide, that when you know attenuation, it relates to the attenuation factor, okay, and how strongly these two surfaces are coupled. So, these are the factors. So, you see that rate constant, it is from 10 to the power 6 to 10 to the power 10, it sharply increases, okay, it sharply increases, and then it decays, okay, then it decays to some value. See that here these are the quinones, okay, these are the quinone type of molecules, okay. For this, you know, it is reducing, okay. So, experimentally if we work with various types of this electron transfer, I mean donor acceptor system, you will be finding that that rate of electron transfer increases, then it reduces. So, it is a remarkable achievement, I mean it is a remarkable achievement that experimentally it has been proved, and experimentally it has been proved that you know the inverted region can actually be observed, okay. Although Marcus already predicted that, I mean means if you look into this diagrammatic representation, you can understand that if you go to this direction, then again delta G double dagger you know increases, and that reduces the rate of electron transfer. So, if you want to, and for this, I mean for this giving this type of model, Marcus was awarded Nobel Prizes in 1992 for his papers or for his work on electron transfer reaction in solution. Okay, so that nicely explains the behavior of this rate constant as a function of various delta G 0. I mean delta G 0 means this gap, okay, as a function of this you know thermodynamic free energy difference between this initial state and the final state. If you want to know more, you can read Marcus's paper in 1955, 56, and also Miller paper in 1984. Okay. And for getting more information, you can also read some standard textbooks which I already have told you. I mean these books, this Lakovich, then Bernard Velour, then Albani, then Nicholas J. Turo. So, these 4 books will be nice to start with respect to this electron transfer reaction and Marcus theory. Okay. So, now what is the general description and what is the explanation? That electron transfer is this factor, I mean this attenuation factor, then a term like delta G 0 plus lambda. So, basically this exponential factor, I mean this exponential factor is taking a great role in determining whether your electron transfer rate will increase or decrease depending on the relative magnitude. Okay. So, depending on the relative magnitude, this factor is the controlling factor, that when when this this is your this delta G0 plus lambda whole square divided by 4 kBt into lambda. So, this exponential factor is very important. The rate should increase as we increase the driving force, driving free energy of the reaction, that is minus delta G0. Okay, that should increase, and this behavior only holds for a small region in delta G0. That is when it is very thin. I mean, when you think of this a thin slice, I mean in this region. Okay. Now, this behavior holds for a small region in delta G0. Instead, the above equation shows that ET rate will increase with delta G0 until a maximum rate is observed for delta G0 equal to lambda. So, if you put delta G0 equal to lambda, then this term, I mean that means this will be equal to 0. So, e to the power 0 means 1. So, this exponential factor becomes maximum. Okay. And then it is a negative term with square. So, that means if it is a negative term with square, that means it will reduce, I mean much faster. So, instead our equation shows that ET rate will increase with minus delta G0 until a maximum rate is observed for minus delta G0 equal to lambda, and the rate then decreases, and this decrease of KET with increased minus delta G0 is known the inverted region or inverted regime. Okay. This inverted behavior means that some extra vibrational excitation is required to reach the curve crossing at the acceptors as the acceptor surface is lowered. That means, so as the acceptor surface is lowered, so some extra vibrational excitation is required. Otherwise, so in order to achieve this extra vibrational excitation, I mean in order to reach this curve crossing, you have to have some extra vibrational vibrational excitation. Okay. So, that actually reduces the, since that extra vibrational overlap, I mean vibrational excitation is required, that actually reduces your KET, I mean electron transfer rate. Okay. Now, Marcus theory implies that barrierless electron transfer can occur if lambda is equal to minus delta G this CS, charge separated state, or maybe means whenever there is electron transfer, then there is in one case there is plus, another case it is minus. On donor it is plus, on acceptor it is minus. So, this is called the optimal region. Okay. So, when lambda is equal to minus delta G 0, and this is called the optimal region. If lambda is greater than minus delta G CS, this electron transfer rate increases with large driving force. Okay. However, in so called Marcus inverted region, if lambda is less than delta G CS, the rate decreases with larger driving force, and this is counterintuitive, and the barrier is very thin in the inverted region, and this facilitates the nuclear tunneling, and thus for the process in the inverted region, that is charge recombination is often an inverted region process is observed, and the observed rates are higher than the expected from the classical Marcus theory. Now, basically what is happening in this region, in this thin region, thin means this is very thin. So, some vibrational overlap of this product surface and the reactant surface, this vibrational wave function, and that actually facilitates the nuclear tunneling. Okay. And these are basically the processes in the inverted region. Okay. So, so if you look into this description, you see that this is your, if you think of a donor in the excited state, an acceptor in the ground state with separated by a spacer. Then this is your reactant surface and this is your product surface. So, this is your reactant and this is your product. So, and this is your lambda, that is the reorganization term, and this is your delta G Cs. Okay. So, this is your normal, this is your optimal case when lambda and delta G Cs charge separated one, these are same. So, exactly it is matching. So, it is a barrier less process. Okay. So, this is the second situation, and the third situation is your this inverted, that this is your lambda, this is your lambda. So, in order to reach this product state, you need to, I mean, since it is over here, so you need to overcome this some vibrational ladder, and that actually reduces the rate of the process. So, this is your reactant surface, this is your product surface. Okay. So, that actually reduces the rate. So, that is why in the inverted region, after after it reaches the maximum, after the rate constant reaches maximum, in the inverted region rate constant reduces. So, this particular thing can be understood, maybe I will come to that in some other lecture, means what is exactly happening, I mean how this electron is transferred and what is exactly happening there during transfer process. With the help of some probability description or probability diagram, we should be able to understand what is exactly happening. But the point is, in the inverted regime, the behavior is exactly something, it is basically a strange behavior. Okay. So, now let us come to another point. I mean, what is reorganization energy? The reorganization energy lambda is the energy, again, I mean this reorganization energy term, I mean this one or maybe this one or maybe this one. So, this reorganization energy is the energy needed to distort the product state and its surroundings to reach the equilibrium configuration of the reactant state. Okay. So, that, I mean, if you come over here, so I mean you have to reorganize the internal as also the external, so that the optimum equilibrium state configuration of the reactant state can be achieved, while staying in the potential energy well of the product state. Okay. The point to which the product state has to be distorted is denoted with the dashed vertical line in the figure. Okay. Now, when the barrier is known and the electronic coupling between donor and acceptor is weak, the rate of charge separation can be obtained using the non-adiabatic expression for the electron transfer as follows. Okay. So, here the electronic coupling matrix element V and the reorganization energy lambda together with Boltzmann constant Kb and Planck's constant and the temperature determine the pre-exponential term. Apart from this, the rate equation is very similar to the well known Arrhenius equation, that is K equal to A into e to the power minus delta G double dagger by Kt, in which A is the pre-exponential factor and reactions are non-adiabatic if the coupling matrix V is smaller than Kb into T, that is the thermal energy, because V in general diminishes exponentially with distance. Okay, like any one electron wave function, the distance dependence of the rate of electron transfer can be described in this way, where where Kc is equal to K0 into e to the power minus beta into Re, where beta is the attenuation factor, is a constant, and it is the scaling scaling the distance dependence, and Re is the edge to edge distance between the donor and the acceptor. K0 is the rate at close contact, that is I mean this 10 to the power approximately 10 to the power 13 per second for barrierless electron transfer. The medium between donor and acceptor strongly influences the rate of electron transfer process through solvation, the value of B. If donor and acceptor are separated by vacuum, the interaction through space is much less. In that case, beta is found to be of the order of this value, I mean 2.8 to 3.8. Then when beta is approximately 1.4 per protein, or a solvent through solvent coupling like benzene, like for benzene beta is 1. Okay. So, if donor and acceptor are linked by saturated hydrocarbon linker, the interaction through sigma bond coupling occurs and can be rather strong. Beta is nearly 0.5 to 0.8, and if a hypothetical graphite bridge is there, then it would be the intervening, if that is the intervening medium, the interaction would be so strong that rate of charge separation recombination would be vibrationally limited at any distance beta equal to 0. But if the energy level of the bridge becomes too low, okay, it can work as a trap for electron and the transfer stops. Here electron localizes onto the bridge. The through bond interaction between D and A is an interaction between electronic orbital of D and A and the orbitals of the linker. Thus, the cis-trans configuration of the bridge and the angles between aromatic units in through pi bond coupling and the presence of orbital coefficients at the interaction point of D and A are of crucial importance. Okay, so in this case, what we have learned is we have tried to understand the basics of this Marcus theory and the expression for the rate constant of electron transfer, the factors that influence this rate constant. We learned the normal region, the inverted region, and how this can be explained in terms of this potential energy diagram. We also tried to understand that. So, in the next lecture we will try to understand this what is called this electron transfer, how this electron is transferred from the product well to the reactant well to the product well, that we will try to understand. So, till then, have nice time. Thank you.